Welcome to our very first lecture on insect vectors and diseases. Today, we are diving into the world of sandfly-borne diseases. We will explore how an insect barely visible to the naked eye can carry devastating pathogens, and we will even use mathematics to understand how these diseases spread through populations. Let us get started. To begin our journey, imagine sleeping under a mosquito net in a tropical village. You might feel safe, but there is a tiny, silent thief that can slip right through that mesh. This is the sandfly. It is only about 1/3 the size of a normal mosquito. Because they fly without making a sound and their bites are initially painless, victims rarely know they have been bitten until symptoms appear weeks or even months later. This stealthy nature makes them incredibly dangerous, acting as biological taxis that deliver devastating parasites directly into the human bloodstream. Now that we understand what this insect is, let us formally define the diseases it carries. In medical entomology, sandfly-borne diseases are illnesses transmitted specifically by the bite of infected female phlebotomine sandflies. The most prominent of these is leishmaniasis, which is caused by a protozoan parasite called leishmania. When the female fly takes a blood meal, she injects the infective stage of the parasite, known as promastigotes, right into the skin. Another major illness is phlebotomous fever. But unlike leishmaniasis, this one is caused by an RNA virus. Understanding these illnesses requires us to study the vector, the pathogen, and the human host. These biological definitions lead us to an important question. Why do we dedicate an entire topic to this one tiny insect? The reality is that these diseases affect millions of the poorest and most marginalized people on Earth. The visceral form of leishmaniasis, known as Kala-Azar, attacks the internal organs, causing massive swelling of the liver and spleen. If left untreated, it is almost always fatal. On the other hand, the cutaneous form creates severe, disfiguring skin ulcers. Even after healing, it leaves permanent scars that cause intense social stigma and psychological trauma. Public health officials must understand this spread to save lives. Before we move on to the mathematics of how this spreads, let us visualize the biology with this diagram. Here we see the complete transmission cycle of leishmaniasis. On the left, the infected female sandfly bites the human, injecting the parasite in its promastigote stage. Once inside the human, these parasites are engulfed by immune cells called macrophages. Instead of dying, they transform into amastigotes and multiply rapidly. When a new, uninfected sandfly bites this person, it ingests these infected blood cells. Inside the fly's gut, the parasites transform back into promastigotes and migrate to the fly's mouthparts, ready to infect the next human. This continuous loop is what sustains the disease. Now that we have seen the biological cycle, we must ask, how do we predict its spread across a whole village? Biologists do not just rely on descriptive words. They use powerful mathematical models. The most critical concept here is vectorial capacity. This is a mathematical value that measures the daily rate at which future infections arise from a single currently infected person, assuming everyone else is susceptible. By calculating this specific number, epidemiologists can predict whether a disease will naturally die out, remain stable, or explode into a massive epidemic. Let us look at the exact formula used to calculate this risk. This formula we just saw is the cornerstone of vector biology. Let us break down what every symbol means. The variable C is the vectorial capacity, representing the total new infectious bites generated per day. The variable M is the vector density, simply the number of female sandflies per human. The variable A is the daily biting rate. Notice it is squared in the numerator because the fly must bite twice, once to get infected and once to transmit. The variable P is the daily survival rate of the fly, and N is the incubation period of the parasite. The denominator represents the natural daily mortality rate of the insect. Crucially, if the survival rate P increases, the value of C skyrockets, meaning the disease spreads much faster. Before we move on, let us see this formula in action with a concrete example. Imagine a rural village where an outbreak is beginning. Health workers find 10 flies per human, so M is 10. The flies bite once every 2 days, making the biting rate A equal to 0.5. The survival rate P is 80%, or 0.8, and the parasite takes 10 days to incubate, so N is 10. We substitute these exact values into our formula. We square the biting rate to get 0.25 and raise 0.8 to the 10th power. After multiplying the numerator and dividing by the natural log of the survival rate, we get approximately 1.2. Because this is greater than 1, every infected person generates more than 1 new infection per day, meaning the outbreak will grow. So we have seen that the baseline disease is spreading. This brings us to a critical proof. Can we prove mathematically that targeting the adult survival rate will stop the epidemic? Let us introduce an intervention. Public health workers spray the houses with an indoor residual insecticide. This does not kill all flies instantly, but it drops their daily survival rate from 80% down to 50%. All other factors, like vector density and biting rate, remain exactly the same. We set up our proof by substituting this new survival rate of 0.5 into our vectorial capacity equation. We want to isolate the effect of this single chemical intervention on the entire transmission cycle. Now that we have set up the equation, let us work through the mathematical reasoning. The most critical part of this proof is the exponential term in the numerator. We raise the new survival rate of 0.5 to the power of 10. This yields a tiny fraction, approximately 0.00097. Conceptually, this proves that almost 0 sandflies will survive the full 10 days required for the parasite to become infectious. We also calculate the new denominator using the natural logarithm, which gives us 0.693. By substituting these back in, we can clearly see how the parasite's long incubation period is its greatest vulnerability when the fly's daily survival drops even slightly. Let us conclude this proof by finding the final result. We multiply the terms in our new numerator, which has shrunk drastically to just 0.002425. We then divide this tiny number by our new denominator. The final calculated vectorial capacity is approximately 0.0035. This is a massive reduction from our original value of 1.2. Because this number is now far below 1, the disease can no longer sustain itself in the population. We have successfully proven mathematically why targeting the adult survival rate of insect vectors is the most powerful and effective way to stop an epidemic in its tracks. We have covered a lot of ground today, so let us summarize the most important ideas. First, we learned that sandflies are highly stealthy vectors that transmit devastating diseases like leishmaniasis to the world's most vulnerable populations. Second, We saw that the biological transmission cycle relies heavily on the parasite surviving a long incubation period inside the insect. Finally, by using the vectorial capacity formula, we proved that even a moderate reduction in the sandfly's daily survival rate completely collapses the transmission cycle. You now understand how medical entomology beautifully combines biology and mathematics to design life-saving interventions. Great job following along, and thank you for watching.